In this video, we're going to be taking a look at something called the well-ordering principle. So recall that we've already looked at weak induction. If a subset of the natural numbers A contains a 0, and for any number, if that number is an A, then so is the next number n plus 1, then you conclude the set is all natural numbers. Now in practice, A was typically the truth set of a statement. If the statement is true for 0, and by assuming the statement is true for n, you can derive the statement is true for n plus 1, you conclude the statement is true for all natural numbers. But we also saw strong induction. If there's some k, so that you can show the statement is true for all indices I up to and including k, where k now is the number of base cases in an inductive proof. And you can also show that for any index past that point, as long as the statement is true for n, it must be true for n plus 1, then you can conclude that, again, the statement is true for all natural numbers. This was strong induction. We've remarked these are logically equivalent. Okay, we didn't actually prove this equivalence, but if you assume that weak induction is true, you can actually prove that strong induction is a legitimate technique. And similarly, if you assume strong induction is true, you can prove that weak induction is. Now, proving strong induction implies weak induction is fairly straightforward. You can actually see if you just let k equals 0 in strong induction, you actually get weak induction immediately. However, proving that weak induction implies strong induction, it takes a little bit of work, but is actually quite doable. So these two statements imply one another. In other words, they're logically equivalent. If you assume one of them, you automatically get that the other one holds. But there's a third statement that's also logically equivalent to these two, called the well-ordering principle, but it does look different. Here it is. If A is a subset of the natural numbers, which is not empty, then A has a least or smallest element. There must exist some element of your set, we're going to call it A prime, so that for anything in your set, that arbitrary element is bigger than or equal to A prime. You can also think of it as follows. There exists a special element A prime, so that A prime is less than or equal to everything in the set. Okay. You include equality here just in case you happen to pick the same element, in which case these would be equal. But in practice, A prime will be less than everything else in the set. Now, this is a very intuitive statement. As long as something is in your subset of natural numbers, there must be a smallest one. Now, as it turns out, you can't actually prove that without relying on an inductive argument. In other words, you can prove this statement is true if you assume, for example, that weak induction or strong induction is true. But similarly, if you assume that this is true, that every non-empty set of natural numbers has a least element, you can use that to prove that weak and strong induction are legitimate. They imply each other, so they're logically equivalent, which means weak induction was assumed as an axiom. Okay, we had the axiom of induction. Since this is logically equivalent to that axiom, if you don't have the axiom of induction, it is not possible to prove that non-empty subsets of natural numbers contain smallest elements. As intuitive as it is, it's not actually provable unless you either assume it as an axiom or you assume an equivalent axiom, such as the inductive axiom. So any non-empty set of natural numbers has a least element, which means you can use existential instantiation. Okay, since this says there exists something in the set where something holds, this is an existential statement, so you can instantiate it. Just be careful, because we're going to do existential instantiation, you must use a variable name that hasn't yet been used in the proof. So if you're doing a lengthy proof and a bunch of variable names are floating around, when you do an existential instantiation, it has to be a new variable. So we can instantiate this smallest element of the set. You can call it n, you could call it A prime, just make sure it's a new name. And knowing that this is the smallest element of the set can be useful for proving things. In practice, you typically want to show that a set is empty. Note that the well-ordering principle says if a set is not empty, then it has a least element. The contrapositive would be if the set does not have a least element, then it must be empty. Okay. If it's non-empty, it has a least element, so if it has no smallest element, then it must actually be empty. It must have no elements at all. So typically, in an inductive argument, we wanted to show that the set on which a statement was true was all natural numbers. For a well-ordering principle proof, you generally want to show that the set of numbers for which a claim is false is empty. So the set A will actually stand for the numbers where the claim is false. If you assume it's non-empty, then it must have a least element. So if you can show that 0 is not in the falsehood set, okay, A is going to be the set where the claim is false. If 0 is not in the falsehood set, then whatever the least element is can't be 0, so it must be at least 1. So whatever the smallest element is, since it's not 0, it must be 1 or larger. Then, since the number n is at least as large as 1, you can subtract 1 from it. If n was 0, n minus 1 would not even be a natural number. So first you say, the claim is not false for 0, so whatever the smallest index for which it's false is, that index must be at least 1, which means there is a previous term. So there must be something before the smallest index on which the claim is false. And then, since n was assumed to be the smallest element on which the claim was false, n minus 1 is not in that set, so n minus 1 must be an index on which the claim is true, and that might be useful. Alternatively, if you can show that the claim being false for n implies the claim is false for n minus 1, then n wasn't actually the smallest element. So by assuming n is the smallest element, and also proving that any time there is an element on which the claim is false, the previous number must also be false, then no matter which number you pick, it can't actually have been the smallest element, which generates a contradiction because there has to be a smallest element. These are two typical approaches to proofs by well ordering. So let's take a look at an example. So suppose I have a recursively defined sequence where a sub 0 is 3, and an plus 1 is always given by an plus 2. Now this should look familiar. We're going to prove that for all indices, a sub n is 2n plus 3. We proved this using weak induction, but we can do a proof using the well ordering principle by doing a proof by contradiction. So assume that there are actually indices on which the desired claim is false. There are some numbers, we're assuming to the contrary, there are some numbers n for which this is not true. Well, the claim is true for 0, so the indices on which the claim is false does not contain 0. We did assume, however, that there are indices on which the claim is false. So there must be a smallest one, because the set of indices is a subset of natural numbers. So if we assume that it's non-empty, that there are indices on which the claim is false, there must be a smallest one. So let's suppose the smallest index on which the claim fails is called n. We know the claim is true for 0 because you can just see it. We were given a sub 0 equals 3, which does match the desired formula. Since the claim is definitely true for 0, the smallest index on which the claim is false has to be at least 1. That little line of argument is just to justify using the index n minus 1. Okay, we need to know that n is at least as large as 1 so that we can subtract 1 from it and still be a natural number. So a sub n was the first index on which we fail, which means a sub n minus 1 is not an index on which we fail. So a sub n minus 1 must actually satisfy the desired formula, that a sub index is 2 times index plus 3. Since n was the first time we fail, the previous index must actually work. But the recursion formula tells us that a sub n is then a sub n minus 1 plus 2. That's this recursion formula, just with our indices shifted. A sub n minus 1 had to be an index where the formula was true, so a sub n minus 1 is given by 2 times n minus 1 plus 3. And when you simplify this down, you get 2n plus 3. In other words, n is actually an index where the recursive formula generates the desired explicit formula. So by assuming n was the first index of failure, n minus 1 is not an index of failure, but that then tells me that a sub n is also not an index of failure, so it's not actually the smallest index on which the claim does not hold. So since n can't be an index where the claim is false, that contradicts the assumption that it was the smallest index. By the well-ordering principle, if the set of failures is non-empty, there must be a smallest such index on which the claim fails. We've shown there can't be a smallest index on which the claim fails. But since any non-empty set has a smallest element, since the set of indices on which the claim fails does not have a smallest element. It must in fact be empty. So since the set of indices on which the claim fails is therefore empty, we can conclude that it is true everywhere. Let's take a look at a second example of a proof using the well-ordering principle. Suppose we have the following sequence. A sub 0 is 1, and for all indices 1 or larger, a sub n is 5 times the previous term squared minus 4. Prove that every term of this sequence is in fact 1. So a sub 0 is 1 was just given, so the claim is definitely true for n equals 0. Let's assume to the contrary, that there is some index on which the claim fails. Okay, note at this point that we are doing a proof using well-ordering principle by working with the set of indices on which the claim fails. Since we're trying to prove that it's always true, we are assuming to the contrary that it fails somewhere. Proofs by well-ordering are very often proofs by contradiction. So we're assuming to the contrary there are some indices on which the desired claim, a sub n equals 1, is not true. Therefore, there must be a smallest index. We're just going to call it n. So a sub n is no longer just a free floating variable. It's now specifically the first index on which our desired claim fails. But we know that our claim was true for index 0. So whatever the first index where it fails, whatever it is, it must be at least as large as 1. So since n is at least as large as 1, we're allowed to use the previous index, a sub n minus 1. Okay. Now, since a sub n minus 1 exists, our recursive formula holds. So this is true because this was true for all indices n at least as large as 1. Now, a sub n is not 1. How do I know that? Because n was the smallest index where the claim fails. Therefore, a sub n is not 1. So 5an minus 1 squared minus 4 is not 1. That's exactly an, so this is not 1. Okay, we can move some things around and conclude that a sub n minus 1 squared is not 1. If a sub n minus 1 squared were equal to 1, well then, a sub n would also equal 1. So by assuming a sub n is not 1, right here, a little bit of arithmetic gets us that a sub n minus 1 squared is not 1, which means it can't be 1, but it also can't be minus 1. Now this is superfluous information. What we conclude is that a sub n minus 1 is not actually 1. So having assumed that a sub n is not 1, we can actually conclude that the prior term could not have been 1 either. So n is not the smallest index of failure. Whatever the index n is, if we assume that an isn't 1, we were able to conclude that the previous term was not 1 either. But we assumed that n was the smallest index where our claim failed. So we've got a contradiction. N is simultaneously the smallest index on which the claim fails, but it also fails at the previous index, so n wasn't the smallest index on which it fails. We've got a contradiction, and the only thing we assumed was that there are indices on which the claim fails. So assuming that there exist indices on which the claim fails led to a contradiction. Therefore, there cannot be any indices on which the claim fails. So since this claim is never false, it is in fact always true. This is a general theme, by the way, that proofs using well ordering tend to be very similar to inductive proofs, but through the lens of a proof by contradiction. Okay, if you look online in other sources, they are also frequently called proof by infinite descent, which can mean something subtly different, but it's a similar kind of idea that somehow you would be able to repeat something infinitely many times, and you can't always decrease infinitely many times in the natural numbers. If I fail at n, I fail at n minus 1. Since I failed at n minus 1, the same argument would give me I fail at n minus 2. This would keep going, and you can't decrease forever in the natural numbers because the natural numbers actually start at 0, which is a good hint, by the way, as to why well ordering is a very specific claim about natural numbers. If we work in other number systems, for example, integers, it's not true that a non-empty set of integers must have a smallest element. For example, if you look at all of the integers, there's no such thing as the smallest integer, because you can always subtract 1 in the integers. So well ordering is a very specific property of natural numbers because they start at 0. But then again, induction is a specific property of natural numbers because proof by induction starts at a base case. Anyway, this is a fairly short video. Proof by using the well-ordering principle is a bit less common than proofs by induction, and because they are all logically equivalent, it's never so necessary to learn one technique over the others, and this one is frequently kind of de-emphasized compared to proof by weak induction and proof by strong induction.